And okay. So here's everything that I have shared with you guys. And you can see on the bottom here, can everybody see where I'm pointing to? So here
Yes.
are all the notes from Unit 1, Unit 2, Unit 3, Unit 4, Unit 5, they're all there. So all the notes from Unit 1, 2, and 3 are here, and all the lessons that we've done so far, I've shared with you. Okay, so lesson 11, I have shared with you. This is that independent study unit, and lesson 12 is what we're doing today. Okay, the other
And sorry, ma'am,
Yes, go
our
on.
midterms gonna be till like lesson 12, or there is
Yes.
gonna be like lesson
Yeah.
13. Okay.
Yeah, so up to lesson 12. So units 1, 2, and 3. So if you see right now, we are halfway through the course. We've done, the course is 20 lessons in all. We have finished up to lesson 10, and we've got lesson 11, which is your independent study unit, and lesson 12, which I'm teaching today. So lesson 11 is very short. I've shared with you, you can go through it. I mean, it's only like 3 or 4 slides long, and then there's the key question at the end. This one, if you choose to do it, is a bonus mark. So if you choose to do it, it's due Sunday, October 24th, together with key question 12. Now, key question 12, that lesson we are covering today. Okay, so lesson 11 and 12, 11 is a bonus if you choose to do it, and lesson 12 is definitely due this Sunday. And then on Wednesday, we do our unit 3 review, and any other questions you guys might have.
But miss, sorry, learning a new like lesson in a week for our midterm is gonna be on Friday, right?
Your midterms on Friday, yes.
Then it's gonna be so hard for us.
I'm afraid that's just the schedule and timetable of this course, the format that you have chosen. It's a very fast moving pace. I understand that. It's very fast. Normally in public school, a lot more hours are spent on this lesson, but because you've chosen to do it in this format here, this is the timeline that we are doing. One lesson is covered during 2 hours, and it moves pretty quickly. I'm afraid that's just the timeline of the course. I'm afraid there's not much I can do about that there. It's a very fast-paced course, very fast-paced course.
Thank you.
Sorry about that, but that's just kind of what you've signed up for here. So, but anyways, I will help out however way I can with any questions you guys have, but if there's no other questions right now, I would like to actually start with lesson 12 because it's pretty involved. It's quite detailed and quite long. So without any further ado, let's begin our lesson on chemical kinetics. Chemical kinetics. So some of the reactions that you might be aware of in the world, such as rusting of iron, they occur very slowly. And some of the other reactions, such as fireworks and explosions, they occur very rapidly, very fast. So why is it that some reactions occur so fast and almost instantaneous, while other reactions are so slow that we don't even notice they're occurring? They take a very long time. So in this unit, we will discuss the concept of reaction rates, how fast reactions occur. And this is a part of chemistry that we call kinetics. Kinetics, as you can probably remember also in physics, has to do with how fast things go. So how fast the reactions go. So chemical kinetics, as I was saying, is a study of how fast or slow a reaction goes, and the pace at which this reaction occurs is called the reaction rate. And the reaction rate is viewed as the change in the amount of the reactants or products sometimes over time. So how much reactants or products the amount are changing over a certain time. The reaction rate is usually expressed as the concentration of the reactant per unit of time, so per second. For example, concentration is usually in the units of moles per liter, and time is usually in the units of second. So reaction rate, the units are moles per liter seconds, and they're always positive by convention, or you can write it as moles per liter per seconds. That's a way of writing the units. So, right, let me just say that, yeah. So the way you write it is your delta C, that's your change in the concentration of either the reactants or the products over the change in time. So moles per liter over seconds, how much the concentration changes over a certain amount of time. So let's look at an example. In this example, the question is, what is the overall rate of production of nitrogen dioxide gas in the system shown below? This is the system that they're talking about, this system shown below, if the concentration of nitrogen dioxide, so that's the product, if the concentration of nitrogen dioxide changes from 0.34 moles per liter to 0.82 moles per liter, so this is the change in concentration, in 4 minutes, and that's the delta T. So we jot down what is our given. So anytime you want to solve a problem, it's good to take stock of what it is that we are given. We are given a delta C of 0.82 minus 0.34 is 0.048 moles per liter. Then we have our delta T. Our delta T is 4 minutes. So the concentration is 0.48 moles per liter over 4 minutes, and it is equal to 0.12 moles per liter minutes. Now this minute should actually be converted into seconds. That would be the more correct way. But just for the sake of simplicity, we've left it as minutes here, but really you want to change this 4 minutes into 4 minutes times 60 seconds per minute, so 240 seconds. So you want to divide this by 240 seconds, and then you will have a proper rate with the proper units over here. So reaction rates are actually not usually constant. They actually change with time. And your delta C over delta T reaction rate is expressed as an average rate. It's another way to determine the average rate of a reaction is by using a graph. We can graph our reaction. And the average rate between the two time points of, say, T1 here and T2 here is equal to the slope of the secant line. This is called the secant line. It joins this point to that point. The slope of the line between the 2 points, and the secant line is defined as a line that intersects the 2 points on a curve. So this would be the average rate. So the average rate would be your change in concentration divided by change in time. And that would be the slope of that line, and that would be the average rate. However, you can also be interested in the instantaneous rate. So not what the average rate of this reaction was between time 1 and time 2, but more like what was the rate of the reaction at this instant, at T1. At T1, what was the rate of reaction? At T2, at T2, what was the rate of the reaction? And that instantaneous rate at any time T would be equal to the slope of the tangent line. This red line is the tangent line to the curve. And the tangent line is just a straight line that touches the curve at a single point and doesn't cross through the curve. That's what a tangent line is defined at. So here at T1, At this point on the curve, the red line is the tangent line, and the slope of that tangent line gives us the instantaneous rate at time t1. At time t2, we draw a tangent line that touches only that point on the curve, and then the slope of that tangent line gives us the instantaneous rate at t2. So there's two different pieces of information between these two graphs. By drawing a secant line, you can get the average rate over a given time, or by drawing tangent lines, you can get instantaneous rates at the given time. Let's look at an example. Let's consider this reaction here, the following reaction. And the question is, what are the reaction rates of the various reactant and products, given that the reaction rate of the iodide ion is 1.2 times 10 to the minus 2 moles per liter seconds. So they're given what's the reaction rate of this. So how fast is this reactant reacting? And they're asking, what's the reaction rate for the rest of the reactants and products? What's the reaction rate for the iodide ion, for the hydrogen ion, for the iodine, for the water? So in order to calculate the rate of these other reactants and products, we have to consider how many moles of each reactant and product. So we say that, okay, so we make sure that, first of all, the equation is balanced. We make sure that there is as many hydrogens on this side of the reaction than on that side of the reaction. So as many hydrogen on the reactants than on the product, as many oxygens on the reactants as well as the products. So first of all, we want to make sure that it is balanced. And then we look at and see, so since 1 mole of the iodate has the reaction rate of 1.2 times 10 to the minus 2 moles per liter, so also 1 mole of iodide should have 1.2 moles per liter seconds. But since we have 5 of them, we have to multiply that rate by 5. And we get 0.6 moles per liter seconds. Same with hydrogen. One of it would have 1.2, same as that other one. But because we have 6 of them, see, we have 6 of the hydrogen ion. So we have to multiply this reaction rate by 6, and we get that value. And so on and so forth. So for the iodine here, we have 3 moles, so it's multiplied by 3. For the water, also we have 3 moles, so the reaction rate is multiplied by 3 again. Okay, is this slide clear to everybody? Does everybody, can everybody follow what this slide is trying to explain? Yes?
Yes.
Yes.
Yes, okay, great. All right, so let's go to the next slide then. So how do we measure these reaction rates? There are various ways that these reaction rates can be measured in the lab, and the method that is used depends on the type of reaction, on the reactant and how the reaction proceeds, and the type of reaction. And there's really 3 main methods that we can talk about here in this course. We can talk about reactions, the types that produce a gas. We can talk about reactions that involve ions. And we can talk about reactions that change color. So in reactions that produce gas, the person conducting the experiment, the chemist, they can collect gas and measure the volume and pressure changes as the reaction occurs to get an indication of the rate. So as you know, gases have a certain volume, they occupy a certain volume of space, and they also have a certain pressure that they exert on their container, whatever is the container that is holding them. So if you can measure that change in volume, that change in pressure as the reaction occurs, you get an indication of how much gas is being made. Generally, the faster the reaction, the greater the change in the pressure or volume in that time interval. Now, for reactions that involve ions, as you know, have a charge. They conduct electricity. So the more ions that are formed, the greater the conductivity. So you can use conductivity, how much electricity is conducted, as a measure of how much ions are being produced, the amount of ions being produced or used up, reactants or products. And in the type of reactions that produce a change in a color, you can choose to measure the intensity of that color using a device called a spectrophotometer, which measures the relative color intensity by shining a beam of light through your sample, and then you can measure how much color change was produced. And that can give you an indication of the amount of reactant or product. So these are different ways that in the lab you can measure reaction rates and follow them. There are some support questions here for you guys to practice with. And so how do we relate reactant concentration, what's the concentration of your reactants or products, to the rate? This is where we have to discuss the rate law, reactant concentration and rate. So let's consider just a generic reaction, whatever it is, that you've got this many moles, let's call it A, lowercase a moles of reactant A, plus this many moles of reactant B, going to give you some product. This is just a very general reaction. Some amount of A plus some given amount of B gives you products. In general, the rate of a reaction increases when your concentration of reactants increases. So the more A you have, the faster the reaction will go. The more B you have, the faster reaction will go. So the rate is proportional. So this is the symbol for when things are proportional to the concentration of your reactant A raised to a power of some number, multiplied by the concentration of your reactant B raised to another power of another number. And this is the way it's proportional, and this proportionality can be expressed in a general equation like this. So rate is equal to some constant K times the concentration of M raised to the, times the concentration of A raised to the exponent M times the concentration of B raised to the exponent N. So this is the general rate equation that expresses the relationship between the concentrations of the reactants, right? These are the reactants, using some rate constant K to give you the reaction rate. So K is known as the rate constant, and the rate constant is unique for each reaction. And the way you find that out is by measuring it experimentally, by doing experiments, and you measure K. Now these exponents here, M and N, are called order of reaction with respect to each particular reactant that it's associated with. So what we mean by that is that M is the order of reaction with respect to reactant A, and N is the order of reaction, this term, order of reaction, with respect to the reactant B. And the sum of M plus N is known as the overall order of reaction, the overall reaction order. And these values for M and N are determined experimentally. And they don't necessarily correspond to the stoichiometry coefficients of the reactants. So if you notice, this is M and N. This is not the same as this lowercase a and b, right? They're not the same. They're different numbers. And they're usually things like 1 or 2, but sometimes they can have even values of 0 or 3. So usually 1 or 2, but sometimes 0 and 3 are also possible. So the values of those exponents, M and N, establish the order of the reaction, so that each of these exponents in the rates law is called the order of reaction with respect to that particular reactant with which it's associated. For example, if you have a reactant X and the exponent of X is 1, so that it's X to the power of 1, then you can say that the reaction is first order because it was raised to the power of 1. It's first order with respect to reactant X, whatever that is. If the exponent of X is 2, so if it's concentration of X raised to the power of 2, then you would say that the reaction is second order with respect to X, and so on and so forth. And the total, or the overall order of reaction, is the sum of the individual orders of reaction. So it's the sum of these exponents here. You add the exponents up and they give you the overall order of the reaction. And these orders of reaction, they can be used to predict reaction rates. Now, suppose you're given this equation. Let's say we're given an equation of 2x plus 2y plus 3z gives us some products. That's the kind of reaction we're given. And we're told that the experimental evidence, so some experiments have been done, and through experimentation, we found that this is the rate law for this product. So somebody tells you, yes, this reaction here, this is the rate law for it, for example. So what does this tell us if somebody tells us that this is the rate law for this reaction? This equation tells us that the rate, R, is proportional to the concentration of X raised to the power of 1. It's also proportional to the concentration of Y raised to the power of 2. And the rate is proportional to the concentration of Z raised to the power of 0. And since we said that the overall reaction order is the sum of the individual orders of reaction, so these are the individual orders of reaction, this 1, the exponents, the 1, 2, and the 0. So the overall order of reaction for this reaction is 1 plus 2 plus 0, which is equal to 3. Now the rate law constant K, right, this rate constant K gives us the magnitude, indicates what's the speed of that reaction. So the value, the magnitude of this K constant gives us the speed of a reaction. And if you have a small k, that means that it's a slow reaction. If you have a large K, that means it's a fast reaction. If K remains constant throughout the reaction under constant conditions, then and K does remain constant throughout under constant conditions, but K then varies with temperature, so that if the temperature changes, K will changes. So the temperature has to be kept constant in all the runs, all the experiments that you do with a given chemical reaction. If you want to determine the rate law for that reaction, you have to keep the temperature constant, because if you change the temperature, you change the value of K. Otherwise, K remains constant throughout the reaction at a constant temperature. So here, note that the rate constant K is actually not a true constant, as I was saying. It changes not only as a result of change in temperature of the reaction, but if you add a catalyst, something that catalyzes the reaction, or if you change the catalyst, if this reaction was already measured in the presence of a catalyst, but then you change the catalyst, you expect that this rate constant will also change. These are factors that will affect the rate constant and then therefore the rate of our reaction. So keeping in mind that this is the reaction that we are kind of considering as our example, as we're trying to understand the rate law. So in this reaction, the rate law R is proportional to the concentration of X raised to the power 1. And raised to the power 1 means first order with respect to X, first order in X. The rate of the reaction is proportional to the concentration of X raised to the power 1, first order in X. If the exponent of the concentration of a reaction is 1, as is the case here in this example, when we multiply the initial concentration by 2, then the rate will also be multiplied by 2 to the power of 1. If we multiply the initial concentration by 3, then the rate will be multiplied by 3 to the power of 1. So however way we change this concentration, the initial concentration, that will be the effect that it will have on the rate. The rate will also be multiplied by 2 raised to the power of 1. And since a number raised to the power of 1 is just itself, the effect is that when we double the initial concentration, the rate will double. When we triple the initial concentration, the rate will triple, and so on. Now let's look at an example where it's raised to the power of 2. In other words, second order with respect to Y. So here you see in this example, Y is raised to the power of 2. So we say that it's second order to the power of Y. So a number raised to the power 2 is the number squared, right? So if the exponent of the concentration of a reaction is 2, like in this example here, if you have this situation here, then when we multiply the initial concentration, then the rate will be multiplied by 2 to the power of 2, because you have this power of 2 here. See over here, it was 2 to the power of 1, because you had power of 1 here. Here, if you double it, it's multiplied by 2 to the power of 2. In other words, 4. 2 squared is 4. If you triple this concentration, if you multiply it by 3, then the rate will be multiplied by 3 to the power of 2, or 9 in other words, and so on and so forth. So that's for second order. For when the concentration of the reactant, it's raised to the power of 2. If for a concentration raised to the power of 0, as in the case, for example, for this reaction, reactant Z to the power of 0, so any number raised to the power of 0 is 1. So if the exponent of the concentration of a reaction is 0, it means that the concentration of that reactant doesn't affect the rate of the reaction. If we double the concentration of the reactant, the rate will be multiplied by 2 to the power of 0, or in other words, 1. won't change. It's multiplied by 1. In other words, the rate won't change. So similarly, if we triple this initial concentration of Z, what happens to the reaction rate? This rate will still not change because it would be 3 to the power of 0. In other words, 1. So in this reaction, the rate doesn't depend on the initial concentration of Z. So we can rewrite this, since in this reaction, Z doesn't seem to affect the rate of the reaction when it's raised to the power of 0. You can easily rewrite this rate law to be R is equal to K x to the power of 1, y to the power of 2. That is what that means. It means Z really has no influence, no effect on the rate. So was that, going through that, was that clear for everybody, or do some people feel like, no, maybe that wasn't very clear? How is everyone feeling? Shadisa, how did you feel? Were you able to follow as what I was saying here?
Yes, I mean, I told you this several times, but I have to like study.
Yes, yes, I get that, for sure. You need to, on your own time, go through this slowly and digest it sort of line by line and make sure you understand it. So I for sure understand that, and that's exactly what I would have to do as a student as well. But what I really want everyone to notice here is that these exponents here on these concentrations of these reactants, so for reactant X, whatever it is, it's raised to the power of 1. That means that that's the same effect on the concentration as it is on the reaction rate. So if the initial concentration of X, which has got a reaction order of 1, if you double it, then the reaction rate will also get doubled. If you triple it, the reaction rate will also get tripled. But if you have a reactant that's got an order of 2, then doubling this reaction, this reactant's concentration will end up quadrupling the reaction rate. Tripling this concentration of this reactant will end up increasing the reaction rate 9-fold, because the relationship is doubled squared or tripled squared. So this is what I want everyone to make sure they understand here from this slide. And I am not going to go into this detail here in this lesson, but if you would like even a more detailed explanation, if you on your own time you can read these next 2 slides. So if you want a more detailed explanation, read the next 2 slides. So this slide and this slide will give you even more of a detailed explanation. But let's go through one more example. Let's go through an example with actual chemical reaction, actual numbers, and see what did I mean by that slide that I was explaining. So let's use this method of initial rates to look at the rate law for this reaction. Okay. In this reaction, we have a rate law that has this form. So the reaction rate is this molecule plus bromine goes to give this molecule plus hydrogen bromide. Now I can't remember what this molecule is, but anyway, it doesn't matter. I think it's, what is it? It's propanol maybe? Yeah, it kind of looks like propanol. So it looks like propanol plus bromine goes to propane bromide and hydrogen bromide. And the rate constant is given by this. Okay, you're told that this is the rate constant, or you know that this is the rate constant to the m to the n, and you're asked using the method of initial rates, which is what we discussed up here on this slide, you're asked to look at this data and calculate the order of the reaction for both the bromide and the acetone. Oh, excuse me, this is acetone. So, right, keeping in mind that molarity, uppercase M, is the molar concentration. So M is equal to moles per liter. So anytime you see this uppercase M, you have to understand that it's moles per liter. I think this is something that I think was covered in grade 11 chemistry, that moles per liter is also given the name molarity, uppercase M, number of moles per liter. And so by that same token, millimolar means millimoles per liter. So here in this experiment, there's 3 sets of experiments set up. And in this experiment, the concentration of bromine was kept at 0.1 molar. The concentration of acetone was kept at 0.1 molar. And the initial rate was this, okay? So then what happened is that they doubled the concentration of bromine, and they kept the concentration of acetone constant. So it's the same concentration for acetone, but as you notice, this has been doubled. So what's the effect on the reaction rate? Let's see, they measured it and oh, look, it looks like the reaction rate didn't really change much. The reaction rate stayed the same. And then let's see, now if we compare experiment 1 and experiment 3, we see that they kept these 2 concentrations the same this time, but this time they doubled the concentration of the acetone. And what happened to the reaction rate that they measured? This is the reaction rate. So in order to calculate the order of the reaction for the bromine, we noticed that the experiments 1 and 2 that held the concentration of the acetone constant while doubling the concentration of bromine, the initial rate of the reaction is unaffected by this increase in bromine concentration. Even though the bromine concentration, look, was doubled, there is no effect on the initial reaction rate. So the reaction rate, is 0 order on bromine, because even doubling it didn't do anything to the concentration. So it's 0 order in bromine. And we can even prove this mathematically by taking the ratio of the rates from experiment 1 and experiment 2. And we say, okay, the rate from experiment 1 and experiment 2, and we write it out and we say it's this and it's equal to 1. Because, I mean, you can see they're the same. Of course, if you divide them, you're going to get the value 1. Now let's look at you can see that they were holding the concentration of everything but one species constant between the 2 experiments so that we could calculate the order of a reaction for a single reactant at a time. So, right, you noticed that they were keeping this and this constant and changing that, or they were keeping this constant and changing that, so that way they could calculate one at a time what is the reaction rate. So now if we look at the experiments 1 and 3, and we can see that because the reaction doubled, so if you can see this value between 1 and 3, this is a doubling, right? 1.64, and it doubled to 3.29 approximately. So it is doubled when the concentration of the acetone was doubled. So here, see, when they doubled the concentration of acetone from 0.1 molar to 0.2 molar, the effect was that the initial rate was also doubled. Yeah. And what does this tell us? This tells us that the reaction must be first order in acetone. So we go back to what we know from what does it mean when something is first order, second order, or zero order? And we see that zero order reactions, there is no change in the rate, no matter even if you double it or triple that concentration. But in first order reaction, if you double the concentration, the rate becomes doubled. If you triple the concentration, the rate becomes tripled. That's how we know that that would be first order for that particular reactant and zero order for the other one. Right. So we write it like that. We say that the rate is equal to the rate constant K times the concentration of bromine, zero order with respect to bromine raised to the power of 0, multiplied by the concentration of acetone to the power of 1. And the overall order of the reaction is 0 plus 1 or 1. So in practice, we probably won't be encountering any reactions that have an overall order of reaction higher than 3. And if once you're done your calculations, you see that your order of the reaction is higher than 3 for a reaction, you are well advised to go back and double check your math because it's very unusual and that it could mean that you have somehow made an addition, some sort of a math mistake. But if you do calculate a fractional power for a reactant's order, that one is quite common, especially half order reactions. And we'll get to some of those. So here we have example 2, a second example. So let's look at that. I'll give you guys a minute just to look at, take a minute, please just look at these data and try and understand what's going on and understand that you can see the way they do this experiment is that they keep a pair of conditions the same while they change the other one. And then in this pair, they keep these two the same while they change the other one. Okay, so I'm going to give you guys a minute to look at what these numbers mean and how they influence the initial rate of the reaction. And then I'm going to ask some questions and hopefully you guys are able to follow along and answer. Okay. Has everybody had some time to look at the data and kind of consider what's going on? Okay, so let's talk about it a little bit now. So this is our reaction, and we can first start out by writing the rate law. So the rate law would be the rate law R is equal to some constant K times the concentration of the first reactant. So there it is, raised to some power M, multiplied by the concentration of the next reactant, raised to some exponent N. So then we want to identify which one of these 3 trials, one second. Okay, so we want to take a look at these experimental data and see in which one of these trials did we change the concentration for only one reactant. So changing the concentration of one reactant. So let's look at trial 1 and trial 2, experiment 1 and experiment 2. And we see that when we compare here, and we see how the concentration of this bromate ion is 2 in trial 2, and it's doubled in trial 1, whereas the concentration of the sulfite is kept the same. Okay, so this is kept the same. This one between here and here is doubled. So we are doing a little bit of like math detective work here. So here to here is doubled. Okay, let's keep that in mind. Let's see what has happened to the rate. Oh, look. The results show that when the concentration of this bromate is doubled, then the rate is also doubled. So this means that it's the 2 to the power of m, that's the doubling part because it's doubled, is equal to 2. So m, which is that exponent, has to be 1. So this must be first order with respect to the bromate ion. So the order of the reaction for the bromate ion has to be 1, right? Did everybody understand how we arrived at the conclusion that since this is doubled, this concentration, when this concentration gets doubled and this is kept the same, the reaction rate doubles? That is indicative of a first order reaction. So it's first order with respect to that product, the product that was doubled and led to the doubling of the rate reaction. Okay, so we figured out what is the order of reaction for one of them, for the bromates. Okay, so we figured out what's our M. Our M is 1. Now let's see if we can figure out for the sulfite. So now let's compare, see, okay, so in this case, these two were kept the same, these two changed. Okay, so now if we compare trial 2 and trial 3, we see that now here, the bromate is kept the same. And from going to trial 3 to trial 2, the sulfite is doubled. So we've doubled the concentration of sulfite, kept the concentration of the bromate the same. What's the resulting effect on the initial rate? Well, it goes from 0.2 to 0.8. Doubled, but here this isn't doubled. This is quadrupled. This is multiplied by 4. It's 4 times, right? So that means that it's doubled to the power of n is equal to 4. So solving for n must be 2, right? So that means the order of the reaction for this sulfate ion is 2. So now we figured out that, n is 2. It's second order for sulfite. So now we can rewrite our rate law as R is equal to K, the rate constant, times the concentration of the bromate, which we figured out was first order, because when we doubled it, the rate doubled, so it's a first order, and times the concentration of the sulfite, and this is to the power of 2, it's second order with respect to the sulfite, because when we doubled it, it quadrupled, so it must be second order with respect to sulfite, and that is how we can write now the correct full rate law for that reaction given the experimental data, right? Okay. And I want everybody to practice these types of questions, and there's some of them in the support questions and in your key questions because they're good to know. Now, there's a part B to this question. So that was part A. Now, so part A was determine the rate law. So we determined the rate law. Now, part B of this question says using your rate law expression, solve for K. Okay, so what is the actual value for K? So we can calculate that by just rearranging the terms in our expression, right? K is equal to the rate divided by this whole thing here. And these values for these concentrations and the rates we have, these are data that's up here. So we can pick really any one of these lines and just plug in the numbers. We can pick line 1. In that case, the concentration of the bromate is 4. So we plunk it in here. The concentration of the sulfite is 6. Plunk it in here. And the value of R is 1.6. If you don't like those numbers, go for the next line or go for the last line. Whatever works for you, but it's going to give you the same K. So pick any of the trials and solve for K. In this case, we'll use the data for the concentration and rate from trial 1. So we just pop in the numbers. And we remember that this one is raised to the power of 2, right? And then it gives us the value for K. If we do our math correctly, this is what it is. And I want everyone to keep in mind that when we do these kinds of questions, these kinds of equations, it is very important to use the correct units. Okay, so that's the units that was for rate, right? For R, the initial rate. This one is in millimoles per liter. Here we changed it into moles by dividing it by 1,000. And then the concentrations in moles per liter. And again, moles per liter. But again, we've changed it to moles because in the table, it was given to us as millimoles. So the 4 then becomes divided by 1,000. So you move the decimal place over 3 times and it becomes 0.004 moles per liter, multiplied by 0.006 moles per liter. But of course, this one is squared because looking back at our rate equation, this was squared. And then we multiply them out and the values that cancel each other. And we end up with this particular unit for this particular K. Okay. And depending on what is the order of reaction for all of the different products, we may end up with units that look different for K values from different reactions, and that will not be a surprise. So just to summarize, I'm sorry, I jumped a few slides. Here's just a brief summary of the reaction rate orders. So for, again, if you have a reactant who, if you change the concentration, in other words, don't change the concentration, the reaction doesn't also change, then that means it's a 0 order reaction. If you double it or triple it, the reaction rate doesn't change. That means it's a 0 order reaction. If you have a reactant that is that when you double it, the reaction rate also doubles, or when you triple it, the reaction rate also triples, that means that that is first order with respect to that reactant, because all of these raised to the power of 1. If you have a reactant where when you double it or triple it, you get quadruple or 9 times the reaction rate, then that means that that is second order with respect to that, because all of these raised to the power of 2 are 1, 4, 9, like that. And the same for third order with respect to that reaction. Then you get when you double that reactant, that concentration of that reactant, you end up with an 8-fold increase in the reaction rate. If you triple it, you'll end up with a 27-fold increase in the reaction rate. And that means that it's third order with respect to that reactant. Now, as I mentioned, the units for K, the order of a reaction can be determined from the units of the rate constant K. And the rate is always measured in moles per liter seconds, as I mentioned. And you have to always remember to associate the correct units with rate and with concentrations. So in a first order reaction, K will have a unit of seconds to the -1. Okay. And so here I've summarized this information in the table. And you can work through it actually and see that once you simplify it, K will have a units of 1/seconds or seconds to the -1 when it's a first order reaction. And varying the total order of the reaction, this is the total order of reaction, keep in mind, will give you the different units for K. And it might be a useful exercise for you guys to go through this kind of a process that I did here for these other orders of reaction to check and see that the units of K in fact do correspond to the proper orders of reaction. There is some support questions for you guys to practice with. So 25, 26, 27, 28, 29, these are all support questions. 30, that's also a support question for your practice. Now, how do you relate reaction rates to time? Sometimes the rate of a reaction in time can be measured by a visible change, by measuring the elapsed time before the visible change occurred. And then the average rate of that would be inversely proportional to the elapsed time, right? It would be proportional to 1/delta T, because that's what rate means. Rate means the change in concentration over change in time. So the rate is inversely proportional to the change in time. Now, what does this mean in terms of half-life? Now, half-life is something, is a concept in chemistry that relates how much of a certain isotope might be left as isotopes decay, as for example, radioactive isotopes might decay in that way. And it's useful to know what is the half-life. Half-life is given the symbol T subscript 1/2, and it's time that is needed for the mass of that reactant or the concentration of that reactant to decrease by 1/2 of its initial value. That's what half-life means. It means how much time does it take to go from whatever was the initial value to half of what it was when it started. So if when it first started, there was 2, at the end of its half-life, it's half of 2, which is 1. If in the beginning of its half-life, it was 30, after its time of its half-life, it's half, which is like 15. So it's whatever was the concentration is equal to the half of the initial concentration. So the concentration at the half-life time is equal to half times the initial concentration. And the SI units, the standard international units for half-life, T1/2, are in seconds, but it is usually expressed in whatever units of time is appropriate to the reaction, because some reactions, it might not be appropriate to discuss how many seconds. It might be more appropriate to discuss how many minutes, how many hours, or how many years even for some isotopes. The T1/2 of any first order reaction is always constant and it depends on the K value, but T1/2 is independent of the initial concentration of the reactant in any first order reaction. Now, T1/2 for any first order reaction can be calculated using this equation. So this is just an equation that relates T1/2, that's the half-life, is equal to 0.693 divided by the K constant K, okay? And the concentration at T1/2 is equal to half of the initial concentration. So let's do an example. Let's calculate the half-life of this radioisotope, this lead-212. We're told that it has a half-life of 10.6 hours. And what is the rate constant for this isotope? So we write the rate equation for this lead-212. We write it as K is equal to the concentration of lead-212, and it's a first order reaction. The T1/2 we're told is equal to 10.6 hours. What is the required, what is the K? What is the rate constant for the isotope? So looking back at our equation that we had on this page, we see that T1/2 is equal to 0.693 divided by K. And so we can just rearrange and plug in our numbers and rearrange for K. So K is equal to 0.693 divided by T1/2. We plug in our numbers for T1/2, and then we have the value for K. And we can write in our statement that the half-life rate constant for the radioisotope lead-212 is 0.64654 hours to the -1, or per hours. Here's a support question for you guys to practice with. You're asked, what is the mass of the radioisotope that will remain after 72 hours or 192 hours, given that it has a half-life of 24 hours and an initial mass of that much? So you're asked to calculate how much is left at the end of 72 seconds and 192 seconds, given that it's had a half-life of 24 seconds. All right. Now, rates of reaction can be explained by what's called the collision theory. Since molecules are held together by the chemical bonds that we've been discussing previously in this course, there must be energy provided to break these bonds, right? And the collision theory explains why some reactions happen faster than other reactions. For reactions to occur, the reactant particles, first of all, need to collide. They need to bump into each other. They need to hit into each other in order for the reaction to occur. And only a certain fraction of these total collisions, these total bumps and crashes that happen together, happen to cause a chemical change. Not every single one of these bumps and collisions is successful at producing a reaction, producing a chemical change. And when they are successful, they're called, well, surprise, it's called successful collisions. The successful collisions have two things going for them. They have, first of all, sufficient energy. They have enough energy. They have enough activation energy at the moment of impact, at the moment that they hit into each other, to break those bonds and form new bonds. So they first of all have to have enough energy, so that there's enough energy to break new bonds and form new bonds and result in forming the product of the reaction. So you can imagine that increasing the concentration of the reactants and raising the temperature will result in more collisions, right? Because first of all, you've got more things, more crowded molecules, more of the reactants, more concentration. So you're going to have higher frequency of bumps, and then raising the temperature. Well, when things get, you add heat to any system, when temperature goes up, there's more energy. Things move with greater energy. So they bring about more collisions and therefore more successful collisions. And that will result in an increased rate of reaction. So there's key points about this collision theory is that, first of all, higher concentration of the reactant particles will increase the number of collisions between the particles per second, and therefore resulting in more successful collisions. Now, for solid reactants, you have to have greater surface area. That would result in more collisions. And then finally, out of all these collisions that happen, collisions must be effective. It must be successful. And to be successful, they have to have the right orientation, and they also have to have the right amount of energy. So here in this little diagram on the side, you can see it's shown that some orientations of collision might not be good orientations, while others might be better orientations that can actually lead to a reaction. For example, if these two molecules bump into each other this way, you don't get a collision. If they bump into each other in this way, you don't get not that you don't get a collision, you don't get a successful collision. It's not effective. If they bump into each other this way, again, nothing, no reaction seems to happen. It seems like it has to be in this orientation and bumping to each other this way. So there has to be enough or the right orientation, and it has to carry with it enough energy, enough of this activation energy in order that will cause breaking and reforming of bonds. So this, out of these different collisions, these different scenarios here, really only one of them is the right orientation and the right amount of energy to lead to an actual successful collision, a successful reaction. Now here I mentioned the concept of activation energy. This has to have sufficient collision energy or activation energy. Let's talk a little bit about activation energy, because orientation is only one factor to bring about an effective collision. But for the reaction to occur, the reactants must also have enough kinetic energy. They have to bring enough kinetic energy, that motion energy with them. The activation energy, which is called, which we give the symbol E score A here, subscript A rather, E subscript A is for activation energy. It is defined as the minimum increase in the potential energy of a system required for molecules to react, okay? So here we can look at these two energy diagrams, which show that for two different types of reaction, one of them is an endothermic reaction, one of them is an exothermic reaction. In an endothermic reaction, you start with reactants starting out with a lower energy, and through the course of the reaction, the products end up with a higher energy. And so there's some energy absorbed here between the reactants to the products. And in an exothermic reaction, it's the other way. You have the reactants start off at a higher energy level, and through the course of the reaction, the products end up at a lower energy. The energy of the products is lower, and there's been a negative change in the energy. Here in this case, energy has been released in order to arrive at this lower energy for the products. So transition state theory is used to explain what happens when molecules collide in a reaction. It examines the transition or the change from these reactants to the products, and the kinetic energy of the reactants is transferred to potential energy. So that energy that they had with them while they were moving is transferred to potential energy as the reactants collide due to the law of conservation of energy, which we have talked about before. So this transition state is what is represented here in these potential energy diagrams. And this hill that is schematically drawn here, this hill illustrates the activation energy. This is the activation energy barrier of the reaction. This is the energy that the reaction must overcome in order to arrive at its products. And in a slow reaction, the activation energy is quite high. So this space here would be big compared to a fast reaction where this activation hill might be lower. So this would be a slower reaction. If this hump was down here, that would be a faster reaction because it has a lower activation energy. And the overall change in the potential energy, that overall change going from here to here, that's the overall change, that's the enthalpy change. It's the amount of energy that has been absorbed in this endothermic reaction, or the amount of energy that's been released in this exothermic reaction. But the activated complex or the transition state, that is the point that is at the very top of these activation hills. Here, this activated complex is neither the product nor the reactant. That is what is referred to as the activated complex up here, or the transition state. Now, what factors affect the rate of chemical reactions? Some of the factors that determine the activation energy that is required for a successful collision in any given reaction is given by, determined by the bond type, the number of bonds, and the bond strength. And also the size and shape of the molecule or the ion also affects the reaction rate. So in bond type, for example, you can imagine that if you have weaker bonds, weaker bonds are broken at a faster rate than stronger bonds because they require less energy to be put in, and the probability that the collision will be of high enough energy is more probable if that energy is very little, if it's a weaker bond. For example, it takes less energy to bring a single carbon-carbon bond than a double carbon-carbon bond. A double carbon-carbon bond, that's a stronger type of bond. It will take more energy. So this type of bond will be broken at a faster rate than this type of bond. Then you can imagine the number of bonds also are one of the factors that determine this activation energy that's needed. Reactions involving the breaking of only a few bonds in that reactant will happen a lot faster than those involving the breaking of a larger number of bonds per reactant. So if your reactant needs to only break a few bonds in order for the reaction to happen, that will happen faster than if you have a reactant with many bonds that have to be broken. And also the bond strength. Reactions that happen between molecules are usually slower than reactions between ions, right? And this is because molecules have covalent bonds, and these covalent bonds have to be broken and new bonds need to be formed. Whereas in ions, there aren't really as many, they're either a single atom, a single ion, or if they're polyatomic ions, typically those bonds don't need to be broken. There aren't any covalent bonds. And this breaking of covalent bonds and forming new bonds this tends to slow down the reaction rate. Finally, size and shape of the molecule or the ion will also affect the reaction rate. Some reactions involve these complicated molecules or complex ions, and these are often less reactive than smaller, less complex types of molecules or ions. And this is partially because there's the more complicated molecules have more bonds that need to be broken. However, it's also less likely that a complex molecule or ion will collide in an orientation relative to each other that will be effective in allowing the reaction to occur. So you can imagine if the shape of the molecule is something complicated with many bonds and many different angles and arrangements and lots of rings and whatever, there's less probability that it will align in the proper orientation to result in an effective collision. So all of these factors really affect the rate of the chemical change. Also, the chemical nature of the reactants. The rate of any reaction, in addition to what was discussed, also depends on the chemical nature of the reactants. For example, metals generally react with acid to produce hydrogen gas. But the rate of the gas that is produced varies depending on the type of metal. So understanding what are the important properties of metals allows chemists to then go ahead and choose that type of metal that will react more slowly if they're trying to prevent corrosion, given whatever is the conditions, for example. So, and also in concentration, generally, if there is a concentration of the reactant that is higher, then the rate of the reaction is higher. And this is really shown schematically in these two diagrams. Here you can see that you have a very low concentration of the reactants A and reactant B. And in this panel, you can see that those concentrations are now increased. So there is a higher concentration of the reactants. So if there's a higher concentration of reactants available for the collisions to form the products, then generally the rate of the reaction is increased. The other factor is the surface area. So if in a solid you increase the surface area, the rate of the reaction also increases. Here you can see here might be a solid that is in one piece, but if that solid is then broken up into smaller bits, therefore increasing the amount of surface area that's available, you can see that that also increases the rate of the reaction. This is a very easy example to relate to, and this is in cooking. For example, if you chop up your potatoes into smaller pieces, you will see that it will cook faster. There's more chance that those hot molecules of H2O can penetrate and get in between the smaller pieces than when you have a ginormous hunk of potato. Smaller potatoes will cook faster than bigger potatoes. Temperature is another factor that affects the rate of a chemical change. If you increase the temperature, that will tend to speed up molecular collisions, and that speeds up the reaction rate. And conversely, if you cool the temperature, that will slow down the reaction rates, okay? So if you look at this graph here, this shows the distribution of how much energy is associated at two different temperatures, T1 and T2. So T1 is a lower temperature than T2. And at a given temperature, you will have only a certain fraction of reactant entities that will possess enough kinetic energy to be equal to exceed the activation energy. So here we're shown on the y-axis is the number of entities, so the number of molecules or ions or whatever is participating in your reaction. And on the horizontal axis is the kinetic energy. So lower kinetic energy, and it gets higher. So for example, if here at this point, this amount of energy at this point, that maybe corresponds, that's where the activation energy is. Remember, activation energy is how much energy you need to overcome that activation barrier to cross over from this transition state towards the products. So if this is your activation energy that's needed, you can see by this distribution on this gas that on this graph, sorry, that only a certain amount of your molecules are going to have that amount of energy or higher in order to successfully react. And as you can see, when T1, which is a lower temperature, compared to T2, which is a higher temperature, for T2, there are more molecules or ions that are capable of making this effective collision. There's more of them that have enough of that kinetic energy to be capable of producing an effective collision. So yeah, so this just shows, based on this maximal Boltzmann distribution, where you have more molecules with enough energy or higher at higher temperature compared to a lower temperature. You can see the green part is a bigger piece under the graph compared to the purple part. What else affects the rate of chemical reaction? Well, let's see, it goes on. If you have a catalyst, now recall that a catalyst is a substance that speeds up a chemical reaction without itself being consumed in the reaction. For example, in our bodies, we have enzymes. These are organic catalysts that help to speed up some of our important reactions that take place in our cells, such as cellular respiration or what have you. And when we eat, for example, our saliva in our mouth releases an enzyme called amylase. And amylase is an enzyme that catalyzes the breakdown of starches into simple sugars. So it speeds up the breakdown of starch into sugar. It's an enzyme, and you can tell it's an enzyme because it has this ending ase. So many of these types of catalysts that are used, that occur either naturally in nature or they may be a part of industrial processes, many of them, their purpose is to speed up chemical reactions without themselves being consumed. So for example, if we look at sort of how much is, if we look at these two graphs, and this one shows, let's look at these two first. So on the vertical axis, we've got the number of collisions of a given energy. And on the horizontal axis is the amount of energy. So here we can see that in the uncatalyzed reaction scheme shown in purple, there is a much smaller number of effective collisions in the uncatalyzed scenario. Whereas in the catalyzed scenario, you have a much larger amount of effective collisions when you have the presence of a catalyst. So you have more effective collisions causing more reaction. But what the catalysts do, they don't increase the number of these collisions between the reactant entities, and nor do they increase the kinetic energy of the entities of the reactants. Instead, what they do is that they provide just a different pathway for the reaction, which as a result will have a lower activation energy, so that the catalyzed pathway, the uncatalyzed pathway will have a very high activation energy, but then the catalyst provides a different energy path that has a lower activation energy. And a lower activation energy means that this reaction is going to happen faster than an activation energy that's a reaction whose activation energy is much higher, much bigger. So this, in the presence of the catalyst, you're going to have faster reactions. And this allows for the reactants to then turn into products at a much higher rate, a much faster rate, even though the temperature hasn't been increased, even though the amount of the concentration of the reactants hasn't been increased. That's what the catalyst does for you. Now let's talk about elementary reactions. What do I mean by elementary reactions? So most chemical reactions occur as a sequence of elementary steps. And then the overall sequence is called the reaction mechanism. So let's look at a chemical reaction for the combustion of acetylene gas to talk about this. So here we have acetylene gas, and it's a combustion reaction. So we know there's going to be oxygen, and we know the products are going to be CO2 and water. Remember, in a combustion reaction, whatever it is you're combusting, whatever it is you're burning is going to burn in the presence of O2 and is going to leave at the end nothing except carbon dioxide and water. So first of all, we want to make sure the equation is balanced. And according to this balanced equation, we see that 2 molecules of this acetylene gas react with 5 molecules of oxygen. And that the collision theory states that these molecules must collide, must actually hit into each other, must collide in order for them to react. But take a look at this. It's really, really unlikely, not a very high chance that you're going to have 7 molecules, because look, it's 7. 2 of these and 5 of these. You need 2 of these and 5 of these to collide together all at once. Like 7 things need to come together and bang into each other at the right orientation with the right amount of speed at the right time. This is really highly unlikely. Instead, what will most likely happen is not that all 7 of these are going to find each other and bang into each other at the exact right energy and in the exact right orientation all at once. Instead, what's going to happen is that this reaction most likely is going to happen in a series of more simple steps, which only at any given time requires the collision of 2, maybe 3 things colliding together at any one instant. Now that I can wrap my mind around. 2, maybe 3 things bumping into each other at the right orientation, carrying the right amount of energy. That is more likely, more possible than 7 things having to bump into each other. So although these steps that we're talking about, these simpler steps, aren't always actually observed, chemists can often predict that sequence of events. So let's take a stab at this prediction. So here are the rate laws for all feasible. Feasible means things that you can imagine as possible. Feasible elementary reactions. For a unimolecular reaction where you have some molecule A going to some product, the rate law would be rate is equal to dependent, some concentration rate constant, and it would be dependent only on the concentration of that product A. say you have a bimolecular reaction. Now, bimolecular reaction, it could either be a molecule of A hitting into another molecule of A to form a product, or it could be a molecule of A hitting into a different molecule B to form a product. And what would those rate reactions look like? Those rate reactions would look like K times the concentration of A squared, or K times the concentration of A times the concentration of B. But for a tetramolecular one, for example, these tetramolecular, meaning three things have to hit each other. It could either be three of the same thing, three A's, or it could be two A's and one B, or it could be three completely different things, an A hits into a B and a C. These tetramolecular, sorry, not tetra, termolecular, excuse me, the term is termolecular. These termolecular elementary reactions are very rare. So for these elementary reactions, notice that the rate law follows directly from the molecularity of the reaction. So meaning that when it's just A going into its product, it's K times concentration of A. When it's A hitting another A, so two A's, the molecularity 2, it's concentration of A raised to the power of 2, because it's A times A. In other words, A squared. When it's A hitting B, the rate is K constant concentration of A times the concentration of B. When it's A hitting A hitting A, three A's hitting together, in other words, K times the concentration of A, three times, it's A cubed. So notice that for each rate law, here it follows directly from the molecularity of the reaction. This is only for these elementary reactions, not this kind of complicated one, but the very simple ones. That's only one or two, or rarely three things hitting each other. And it's important to remember, however, that we cannot tell by just looking at the balanced overall chemical equation whether the reaction involves one step or several elementary steps. It's hard to tell. You can't just look at it and see. Now, for elementary reactions only, what I'm talking about on this slide is for these elementary reactions only. For elementary reactions only, not for reactions with an overall balanced equation with a detailed reaction mechanism. So not for things like that. No, not for things like that, but things for elementary steps like this one. The coefficient for the reactants are the exponents in the rate equation, right? So remember, in a unimolecular reaction, if you have one A going to the product, then it's the rate law is first order. So rate is equal to rate constant K times the concentration of A. The coefficient 1 becomes the exponent. Or for the bimolecular reaction, the rate law is second order, so that the rate is equal to the rate constant K times the concentration of A raised to the power of the coefficient in front of it in that reaction times the concentration of B raised to the power of that coefficient. Or if it's 1A times 1A, then it's A squared. Or if it's 2A going to products, then it's, again, A squared. And for the rare termolecular collisions where it goes something like this. So let's look at an example together. Let's see how much more. Okay, we are almost done. Okay, good. So for example, let's look at the example where we have nitrogen monoxide. So here it is. Nitrogen monoxide, NO gas, reacts with oxygen according to this equation. Now, this reaction doesn't occur in a single step, but rather through these two steps, right? The elementary steps involving 3 reactant molecules are very rare. Remember, we said that if you've got 3 things bumping into each other, that's really rare. Probably not going to happen. Let's not consider it as something that happens very typically. They're rare. Okay, those kinds of situations where you've got 3 things hitting into each other are rare. Just want to emphasize that. They are rare.
Sorry, Miss, can you let me in? My iPad is dying, so I just wanted to. Yeah, thank you.
Yeah, no problem. So yeah, those things are rare. So if we look at this, again, you've got 2 NO gas hitting 1 O2 molecule. So 3 things hitting into each other. That is probably not going to be an elementary step. It involves 3 reactions, 3 molecules hitting into each other. Very rare. Why? Because according to the collision theory, a chemical reaction must involve collisions of chemical entities with each other or the walls of the container sometimes. And if we just think about this logically, just think about it. And also calculations show that collision of 3 things simultaneously will be a lot less frequent than the collision of 2 things hitting each other simultaneously, okay? So we say that, okay, this is probably not the elementary step. It probably happens through single steps, through these types of single steps. Maybe you have 2 nitrogen monoxides colliding together to give this N2O2. And then the N2O2 might collide again with the oxygen to give 2 NO2s. So most of these reaction steps would have either 1 or 2 reaction entities. And these reaction steps then involve only 1 reactant entity, includes those which a single entity collides with the side of the container. So it could be that it's if you have 1 thing, for example, that example I gave of A going to product, how does A go into a product without bumping into another A? Well, A can go into a product bumping into the wall of the container, for example. It might collide with the side of the beaker, for example, with enough energy. So, so if we say, okay, maybe it happens through something like this, and we notice that if we add these 2 reactions together, then these N2O2 factors cancel each other out, and we will end up with our overall reaction that is what we had up here before, what we started out with our target reaction. So this dinitrogen dioxide cancels out, and it doesn't appear in our overall equation anymore. And these kinds of substances are called the reaction intermediates. So that this N2O2 would be what would be considered an intermediate. So it's made in step 1, it's used up in step 2, and they're very short-lived because, as you can imagine, they're made and they're immediately used up in the next step. They're very short-lived. And that given an overall reaction, it's not possible to predict what the reaction mechanism would be, but if you are given the steps of a reaction mechanism, you will need to be able to add together these individual steps to end up with the overall reaction. So if you're given these steps, you need to know how to add them up in order to end up with your overall reaction. So then we need to figure out, so which one would be the rate determining step? Because obviously these might not be happening at the exact same rate. So which one is the rate determining step? So here we have another reaction mechanism with some additional information about the relative rates of each of the individual steps. So here, for example, we're given that the overall reaction is this, and you're given that step 1 is this kind of thing, HBr, hydrogen bromide goes to O2, goes to HOOBr, and then that HOOBr is the reaction intermediate that gets used up in step 2, collides with another HBr and produces 2 HOBr molecules, and so on and so forth. In step 3, we have this. In step 4, we have this. And if we add all of these up and our reaction intermediates cancel each other out, we end up with our overall reaction. So these are the and what's proposed as the individual steps that will lead to this overall reaction, because it's highly unlikely that you're going to get 4 of these and 1 of these, 5 molecules colliding with each other simultaneously at the exact right orientation and the right energy to produce a reaction. No, chances are it's happening through a bunch of smaller, more simpler elementary steps. And here we're told that this first step is very slow, is a slow step, and that the next 3 steps are fast. Now, we don't have values for the actual rates of these individual steps, but here's a question for you to consider. Would you consider the overall reaction now to be fast or slow? Now you're given that this one is slow and these 3 are fast. So would you think that this overall reaction now that we have on the bottom, would you think that this would be a fast or a slow reaction? What do you think? With 3 fast steps and 1 slow step. Okay, what do you guys think? Borna, what do you think? Do you think if you start with 1 slow step and followed by 3 fast steps, what will you have? A fast or a slow, and why? So Borna, Judy, Sasan, and Shadisa, each of you go ahead and chime in with what you think. No right or wrong answers. Let's just discuss so that we can just have a better discussion on rate determining steps. Okay, who wants to go first? What do you think?
I think it's because it's just like it started slow, but it's keep going fast. So I feel like it's gonna be fast.
You feel like it's going to be fast, okay?
Yeah.
So Sasan thinks it's going to be fast. Anybody else agree with Sasan or disagree with Sasan? And tell me why. Tell us why. Anybody agree with Sasan or anybody disagree with Sasan? Does everybody think this is going to be a fast reaction? The first one's slow, the next 3 are fast. Sasan thinks this will be a fast reaction. What do the rest of you think? Okay. Okay, so let's just consider. So let's say the first step is slow. Let's say the first step takes a year to do. The first step is such a slow step, it takes a year for this to happen. The next step is so fast, 0.1 seconds. The next 2 steps are pretty fast too, 0.1 minutes and 0.1 minutes. Overall, at the end, with these 3 fast steps and only 1 slow steps, most of you would probably guess just like Sasan did, that overall this should be then fast. But think about it. It's going to take a year for this thing to happen because the first step is what takes a year. So it doesn't matter that these next 3 are happening super fast. We still have to wait a whole year for this to happen before we can even hit these ones, right? So the overall rate of any reaction depends on the rate of the slowest step, guys. It's the slowest step that determines the overall rate of the reaction. And this slowest step is called the rate determining step, right? So it's the rate determining step determines what's going to be the rate of the overall reaction. And that is always the slowest step. So this reaction up here, step 1, is the rate determining step. And that's what ultimately decides the overall rate of the reaction. If you want to speed up a reaction, this is where you put your focus. You want to increase the rate here. You want to make it happen faster than a year if you want to speed up this thing. This is where your focus should be, in this rate determining step. So these rate law equations that we write from these elementary steps, these are the elementary steps. These rate law equations can't be written using the information from an overall balanced equation for a reaction, but rate law equations can be written directly from the balanced equations representing the elementary steps. So examples of some of these common types of elementary steps and the corresponding rate laws are shown in the table. So we did actually go through these in a couple of points during the previous slide. If you, this should be a very familiar concept to you now. We talked about it here, and we talked about it here. And we're showing the table again over here. So although you can't say what the rate law is going to be for this equation, or even for this equation just by looking at it, you can tell what the rate laws for these elementary steps are going to be just by looking at them. You can tell for step 1, step 2, step 3, step 4. You can say it for those. You can figure out the rate law for those just by looking at them. So you can use that to then determine the rate law for the overall reaction. But first you have to do is you have to first propose and evaluate your mechanism. So how are you going to do that? So first you have to write the equations for the elementary steps in such a way that they combine to give the overall equation. And the second is that the proposed elementary steps must be reasonable. Like you can't have no more than really 2 reactant molecules hitting each other. Because once you get into 3 and more, it's just not reasonable that you're going to have 3 molecules with the right energy, the right orientation, hitting each other at the right time, at the exact same time, at the same instant. And thirdly, the mechanism must support the experimentally determined rate law, so that one elementary reaction is when one elementary reaction is much slower than the rest, then that's the rate determining step, and that the rate determining step can occur anywhere in the reaction mechanism. It's not always the first step or the last step. It can happen anywhere. It can be first, middle, last, anywhere. And where you have a fast step coming before a slow one, we can solve for the concentration of the intermediate by assuming that an equilibrium is established in the fast step. So let's try an example. Let's try the decomposition. So breaking down, decomposition means breakdown. The decomposition of a molecule of dinitrogen pentoxide. So here we have dinitrogen pentoxide breaking down to dinitrogen, I guess, tetroxide and a molecule of oxygen. So the question is, what would the rate equation be? What would it be if the reaction occurred in a single step? So in this case, the rate equation would be the same as the coefficient on the reactant, right? If this happened in a single step, therefore the rate law would be, it would be the concentration, the rate would be equal to the concentration of rate would be equal to the rate constant K times the concentration of this dinitrogen pentoxide. And since you have two of them, multiplied by the concentration of dinitrogen pentoxide. In other words, the concentration of dinitrogen pentoxide squared, right? Since you have two of them, right? If we assume it's happening in a single step, and that this is like an elementary step, the rate law would be something like this. But suppose you're told, actually, no, it doesn't happen like that. What happens is the rate law is actually this. What we've measured, those experiments that we did, tell us that the rate law is something more like this. Then what would be your rate determining step? Now, because the coefficient on the reactant must be the same as the exponent in the rate equation, the rate determining step must be that you have one N2O5 going into some intermediate product. Oh. Okay. Must be going into some intermediate product. So most reaction steps have either one or two reactant entities. Reaction steps that involve only one reactant entity include those in which the single entity, again, I'm repeating this, collides with the side of the container or the beaker and then breaks apart into smaller entities. So suggest a possible mechanism for this reaction, okay? So let's say that, we suggest this, okay? So let's say that we have N2O5 going into N2O4 plus O, which is our slow reaction, and the oxygen then collides again with another N2O5 and gives us N2O4 plus another oxygen. So in this case, we have to choose, so which one is the fast, which one is the slow. Now remember, the fast step is never our rate determining step. It's always our slow step that is our RDS, that is our rate determining step. And the second point is you don't want to have a reaction intermediate as our reactant in our rate equation. So we want to make sure that when we write our rate equation, the rate equation has to be determined by the rate determining step. So the rate determining step must be, the slow step must be this one. It cannot be that one, because then we're going to have, this would be our reaction intermediate, right? It's being made here and used here. So we don't want it to be this. We want it to be this one. We want it to be the slow, right? We don't want this single O to appear in our rate reaction. So actually this is very important. This is what we don't want, and this is what you have to remember. I guess it's highlighted enough, right? So if here, I don't know if everybody understood this. Let me explain this one more time, okay? Because yeah, we just have a few more minutes and I just want to explain it one more time. So also, before I explain that a second time, if you would like a more detailed explanation again, if you want to read a little bit more, read this slide and read this slide. These are the next two slides. But let me just go over this point one more time, okay? So suppose you're given this reaction and you're told that the rate law for that reaction is this. And you're asked then, what are the elementary steps and which one of those elementary steps is the rate determining step? Now, remember from our previous slide, we said that the rate determining step is always the slow step, whatever one is the slow step. So here we're going to see, okay, because, so we try and imagine what could happen. You could have this N2O5 decomposing into N2O4 and another oxygen. And then that oxygen colliding with another N2O5. So here now we have two N2O5s, just like we had in our target sequence. And then it decomposing into another N2O4. So here now we have our two N2O4s and our two O2s. And not our two O2s, our one O2, down here are O2. Okay, so we say these are the elementary steps, and we know that they're okay because this O cancels out with this O, and we have two N2O5s adding up together on the reactant side, two N2O4s on the product side, and one O2, right? If we add this all up. So now we just have to choose, is this slow one or is this the slow one? Which one's slow, which one's fast, okay? So we can't choose this as the slow step. We have to make the choice of this being the slow step. Because why? Because it's the slow step that determines the rate, right? If we chose this to be the rate determining step, let's say we said, oh, this is going to be our slow step, we would be wrong because, first of all, a fast step is never our rate determining step. So it's definitely not this one. But let's say we made a mistake and said, okay, this one is a slow step. If we were to write the reaction rate for this step, it would look like that, right? It would be the concentration of O multiplied by the concentration of N2O5. That would be wrong because we never want to have the concentration. We don't ever want to have a reaction intermediate. See this oxygen here? That's a reaction intermediate. It gets made here and used up here. We never want to see a reaction intermediate in our rate equation. And besides, this rate equation is not what we're getting here. If we choose this step to be our slow step, then it becomes our rate determining step. And if we did try to write the rate law for this, it looks something like that. And that's how we know now we've got it right. And this is our rate determining step, this is our slow step, and this must be our fast step. Okay. All right, so I completely understand this was a very full lesson. We covered a lot of grounds. There's a lot for you guys to do between now and the day of our midterm. Please practice with your support questions, like starting tonight. Do your key questions. Those key questions that you guys have been doing and handing to me has not been for nothing. It has been for grades towards your course, of course, but also it has been preparation. You've been getting practice. You've been trying these types of questions. And I have marked all of the questions so far and returned them to you. I haven't marked yet what you guys handed in last night. I will mark those and have them into you by tomorrow for sure, so that you can go into your shared folder and look at your test, your assignments, and see how you did, what mark you got, what mistakes you made. If you have questions for me about those assignments, why did I not get this question correctly? What mistake did I make? Where did I go wrong? How do I do this correctly? Talk to me about this and I will help you out. Or do more reading and find out and look into your book. On Wednesday, I will recap, do a review of all of our Unit 3, that is lessons, what is it? 8, 9, no, it's the lessons 9, 10, 11, and 12. I will do a review of these on Wednesday, and I will answer any questions you guys have on units 1 and 2. So we can do any questions from unit 1 and 2. And your test is on the Friday evening. Between now and then, if you have any questions for me, if you need any time with me, please let me know, and I will do my best to help you over email or during our review session. Okay. Everybody have yourself a good night. Okay. Thank you so much. Thank you.
Bye-bye.
Bye-bye.
Thank you. Have a great night.
Thank you. You too.
Goodbye.
Bye.
Bye, Miss.
Bye. Good night.